Hey guys, Sun here. I'm a privacy and security researcher and you're watching Behind the Scenes. In today's episode, I want to go back to last episode, how to back up and encrypt data privately and securely using rsync and VeraCrypt on macOS. I want to share with you guys my train of thought when considering how to do those backups. By the way, everything I share on the privacy guides, well, that's the stuff that I'm using for my personal data and I take that very seriously. So, by the way, all of the reference material that is shared is alive. That means that updates will be done to it over time. I kind of need your feedback on a problem that I have. Since YouTube videos are kind of permanent and the reference material is not, meaning that it is updated over time, how can we synchronize both? How can I do this? I mean, that's why I'm using a behind the scenes today. Maybe you guys have better ideas, drop them in the comments. But yeah, since I published this episode, there were still a few things that I was not happy with, that I was worried about. Now, I'm going to go through those today and explain why I feel comfortable with the updated guide. Now, if you did follow the guide, you may want to go through it again using the updated guide. A few things have been hardened and the guide has been peer reviewed. More on this at the end of today's episode. Okay, so the first thing that I was worried about is something called data degradation. Storage devices such as spinning hard drives, SSD hard drives, flash memory, CDs and DVDs, all of these different types of storage have a lifespan. When you put data on a spinning hard drive, it won't work, it won't be accessible forever. Data degrades over time, and that is true for all storage devices. Now, a problem with some encryption algorithms is if some part of the encrypted data becomes damaged or degrades, well, the whole data set becomes corrupted, and that's really bad. To mitigate that, both VeraCrypt and actually FileVault on macOS use an encryption mode called XTS, and the way that works is it chunks all of the data in little blocks, and each block is encrypted individually. That means that if one block becomes corrupted, only the data within that block is lost. So that really made me feel good about storing stuff using VeraCrypt. Now, another thing that I was worried about is cryptanalysis vulnerabilities. So, encryption algorithms or hashes from the past have been broken. So I don't like the idea of encrypting information in a way that might be broken in the future. Something that VeraCrypt suggests to mitigate that is called cascading algorithms. So it's possible to use more than one algorithm to encrypt the data. And that means that even if one of the encryption algorithms is broken in the future, well, the data is safe. So that's something that I updated in the guide. So again, please have a look at the updated reference material. Now, another thing that I'm very worried about is quantum computing vulnerabilities. So a lot of researchers, funded in the millions and millions, are developing quantum computers. Without going into a lot of detail, quantum computers are new types of computers that are capable of computing mathematical problems really, 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 really fast, much faster than even huge clusters of computers are capable of doing today. Now, the thing with that is, a lot of the encryption algorithms use maths behind the scenes, and if those computers are capable of, going through huge mathematical problems really fast, well, those encryption algorithms might be broken in the future. Now, VeraCrypt uses 256-bit AES for encryption. The good news is, according to most security researchers, quantum computing will actually have the security of 256 bits to 128 bits, which is still considered secure by NIST, the National Institute of Standards and Technology. So that means that the way we're encrypting stuff with VeraCrypt will likely be post-quantum computing compliant, which is good. Now, another thing, and now we're getting into more quirky things, but they're actually very important. We're leveling vulnerabilities. When we use flash memory, and that applies to SSD hard drives, it applies to USB thumb drives, the way those devices work is each sector, or I don't know if that's the right word, but each little piece of memory can only be written to X amount of times. Once it's been written to more than X amount of times, it starts failing. That's why early SSDs were really shitty and tended to become corrupt really fast. To mitigate that, those pieces of hard drive use something called wear leveling. That means that instead of writing data over the same block of data each time, it will write the information over the whole SSD. That means that, say we overwrite a file here, well, instead of rewriting the data here, it will use a block that has never been written to here. That means that the information can potentially be read in 2 locations now. Why is this important in the context of VeraCrypt? Well, it's very important because if we go about changing our password, remember at the beginning of the episode, I said that the headers, actually I hope I said that in this take anyways, VeraCrypt will use a master password to encrypt the data. The password that we enter is essentially a way of encrypting that master password that never changes. So that password that we use to encrypt the master password, if that piece of information is overwritten, that's how VeraCrypt would do things normally. Well, it might not be overwritten when wear leveling is active. It might essentially keep the header here and kind of recreate the header somewhere else. That means that an attacker that may have found the password through XYZ way, well, that attacker might be able to use the old header to decrypt all of the information. That is why we really have to be careful when using flash memory. Now, flash memory is amazing. We just have to keep in mind that we cannot change the password in VeraCrypt on flash devices without it being vulnerable to this kind of attack. Another thing we have to keep in mind is we shouldn't use journaling file systems. So on macOS, using macOS Extended, for example, or APFS, those file systems are journaled. That can lead to metadata leaks. So VeraCrypt recommends formatting volumes using FAT, or if we need to have a larger volume that is larger than 4 gigabytes, using exFAT. And I've been testing things with exFAT and it works very well. So that's another thing that I've updated in the guide. Okay, moving along to one thing that I didn't even know existed. I feel kind of naive here. Most encryption algorithms do not do something called authentication or data integrity by default. And that is the case for XTS. What I mean here is if someone tampers with the VeraCrypt volume at the bit level, that person could potentially delete part of the information, or at least render it gibberish, part of the information without us never being aware of it. When I was studying Borg, which is a backup solution, which is open source, more on this in a future episode probably, when I was looking at Borg, they use a way of having both encryption and authentication, which leads to being able to validate if the integrity of a backup is good. What I mean here is, if we take all of the blocks that are encrypted, and if we, for instance, generated a hash for them, which also includes key material that makes it authenticated, meaning only us can generate that hash, it's possible to compare the block with its hash. Now, for those of you who are new to hashing, hashing means we take a chunk of information, we run it through a hashing algorithm, and it will generate a pretty short string of characters that is unique to what was inputted in it. Now, a way of doing this that is secure, and that's the authentication layer, is if that hash function also takes a password or a secret, well, it's possible to generate a hash that only us can generate. So even if someone has access to the data, they cannot recompute this without this little secret, which cannot be reverse engineered theoretically. So that is what Borg does. In the context of VeraCrypt, none of this is being done. Same for FileVault on macOS. The reason is pretty simple. If for every file, every bit of data we had on our computer, in the context of FileVault, if we also had to compute and store hashes, that would increase the space, the amount of storage required for this data, and would slow things down. So that really doesn't apply in the context of full disk encryption. And VeraCrypt really was engineered having in mind full disk encryption or large volume encryption. So that's why they don't do this. Now, thankfully, there is a really simple fix for this. We can take our encrypted volume, which is essentially a file, and feed it to a hash algorithm, and it will generate a hash that is unique to a current state of the backup. And that's something that I also implemented in the guide. And thanks to Alex, by the way, who is now a contributor to that guide, I learned a lot about hashing and how to make those things more secure. So essentially, at the end of a backup cycle now, the script that we have in the reference material will suggest generating a hash, which we can then store in our password manager. And when we, for instance, take a backup, such as our little card here, if we take a backup that's on an SD card or a little flash drive, and we store it in a safety deposit box, or we store it at a friend's house, when we get it back, we can actually run the hash against it to see if data has become corrupted or if someone has tampered with the backup. So that's a really great way of adding integrity checks. And it kind of works, it kind of does it for authentication as well, because since we're putting the hash in a password manager to which only we have the password, well, we're the only person in the world that's capable of comparing both hashes. And a script, by the way, was added to the guide to facilitate comparing hashes. Maybe I'll demo this at the end of this episode, actually. So yeah, one more thing. Once everything that we just mentioned has been implemented, there still is one weakness in the system, and that's human error. If we delete a file by mistake, or if a virus deletes a file by mistake, or that's not by mistake actually, but if a virus deletes a file, we want to be able to go back in time and grab that file. That's how Time Machine works. Now, thankfully, rsync has a bunch of arguments that we can feed to the command line stuff that are for backups. And what I did now is when we go through the backup procedure, what happens is each version of a specific file is replicated and stored with a specific timestamp added to it. And that means that we can go back in time if something has changed. And that's super powerful. By the way, it's not at all efficient from a data storage perspective, but the purpose of this guide is to keep things really simple and have as few layers of extraction possible to make sure that those keys that we're storing are accessible, etc. Okay, so before moving along, I'm going to demo how this updated guide works. So if we go here, I added a bunch of disclaimers and stuff. I added instructions on how to install Homebrew, GPG, but all of this is done. What we want to do now is essentially recreate that backup that we did in last episode. So I'll use my little USB stick here to show you how this works. Okay, so as you can see here, there are no files on the USB drive. If we open Disk Utility, the first thing that we want to make sure of, we want to make sure that the Samsung bar USB hard drive here is formatted using exFAT or FAT. I recommend exFAT because, there's no reasons why we would want to use FAT, which has a 4 GB limit. So you want to make sure that it's formatted to exFAT. If it wasn't, you just click on Erase, select exFAT, and go about erasing the drive. Good. Once this is done, we can move along here with the steps that we followed in last episode. So I'll pop open a terminal, and I'm going to run the first command here. Now we want to go about generating the VeraCrypt encrypted volume. Let me put this a little bigger. Okay, so normal, the size, I'm going to create a 1 GB container. This is one of the things that has changed. I now suggest using 7. Now SHA-512 is perfectly fine. We want to use macOS extended when the backups are done on macOS. Now I'm going to put a really shitty password. Yours should be much, much longer and skip PIM and keyfile. Now I need to type in a bunch of gibberish on my keyboard. Sorry for this little moment here. So what we're doing here, by the way, I'll explain this while it's being created. What's happening here, the reason why we're typing all of this crap on the keyboard is as I mentioned earlier, the way VeraCrypt works is it uses our password to encrypt the master password. The master password never changes, and the master password is what encrypts all of the blocks in a VeraCrypt container. So volume, sorry. So that's what we're typing here. We're generating entropy, randomness, to create the master password, which is then encrypted in the headers that are stored both at the beginning and the end of the volume using our password. So while this here is happening, let's move down to the next steps. Wow, we still have a little bit of time here. Probably going to fast forward this in post. All right, so the volume has been successfully created. The next step here is we want to mount it and rename it. By default, sorry, shitty password, by the way, yours should be much longer and much more random. By default, encrypted VeraCrypt volumes are called untitled. I rename it to backup just as some kind of a convenience feature here. Okay, now we're going to create the backup script. So there's a few things that have changed. First of all, it's now more tolerant to being canceled using Control-C. So when you cancel it, it will dismount the volume if necessary. Now all of this here is the same as before. This is the same as before. Now here things have changed. We now enable backup dir, and added a suffix for the versioning stuff. Now this here is another change. The script will ask us when different versions are more than 90 days old if we want to purge them or prune them, I should have said, from the system. That will keep the backup size small. Now all of this has changed. This here is different as well. This here will ask us if we want to generate a SHA-512 hash that we can store in our password manager. And that's a really neat way of making sure that the data integrity is okay. Okay, so we want to take all of this script. Oops. And we want to run it here. Now we want to go about editing this. So I'll go here. Actually, just for the purpose of today's demo, I'm going to go on the desktop and I'm going to create a file called test, in which I'm going to write foo. Now, while we're editing this, okay, I am going to add that file test, and I'll show you guys how versioning works. So that's interesting here. Once this is done, I also added a check script, and that will compare hashes. I'll show you guys what this looks like in a second. All right, so we're now ready to do our first backup. By the way, if you guys followed the old guide was created in a way that required sudo, so it required admin privileges. I kind of didn't like that finally. So one thing that you definitely want to check is, let me see here, perhaps you have a conflicting version of the script. So if you write the following command, sorry, this is not in the reference material, but okay, if you write the following command with sbin, and that actually returns an existing file, you want to make sure that you run rm, which is remove, it deletes a file, user/local/sbin/backup. Actually, I'll add that command in the comments on YouTube, because you don't want to run this and kind of like delete files that are not what you think you're deleting. That's actually kind of a dangerous command. But if you go about deleting exactly this pat here, that will make sure that you don't have the conflicting version of the backup script on your system. If you have questions about that, drop them in the comments. By the way, I know this is a bit confusing. Okay, so now we can go about running our first backup. So again, super shitty password. Yours should be much longer. Okay, so once this is done, the backup has been done. It asks us to inspect it. That's something that I really like because of the way this uses Fuse. We can actually navigate the backup using a file system that we're familiar with. So we can just kind of go in users. We can also click on command. What's this key here actually in English? Shift, yeah, command shift L to command shift dot, sorry, to show hidden files. So now we can see that we have all of this. We have our desktop and the test. Now the content of test, let's see, if I open this with Visual Studio Code, you could open this with any text editor actually. Network, no. Okay, so we can see that the content of it is foo. Okay. So once we inspect the backup, we just type enter. And then the next step, it will ask us to generate a hash so we can say yes. So what's happening here is it's taking as an input that B file, so the file that includes the encrypted volume, and it generates a hash for it. So that hash here, I'll store it in a file just so we can reference it later, okay? Now, let's say we edit test and we now, instead of foo, we say bar. Okay. Okay, I'll have to cut this in post-production actually because I didn't authorize, well, we'll do it like this. So Visual Studio Code is asking me for permission to change files on the desktop, and I said no. So if I go in privacy, and then I go in file and folders, I won't allow, it to access this. Okay, so bar. Now that this is done, if we rerun the backup, there's a few things that happened. So now if we go in versioning, we go in users, sun, desktop, test. If we look at the content of test, we'll see that the content is foo. Now that's because we're in the versioning backup version. Whoa, that was a weird thing. If we go in user, sun, and then we look at test, we'll see that this here is bar. So as you can see, we have both versions of the files. So if that was, say, a backup of your password manager, and somehow you deleted it from the computer and then ran the backup and it was deleted from your backups as well, well, at least you have this version, thankfully. Okay, so once this is done, we'll hit enter. Whoops, sorry, I have to get out of here. So I'll just say yes. That's because I had a window open with this file open. Okay, generate hash, yes. All right, so this here is the new hash. So as we'll see, the hashes are not the same. And the reason for that is each time files are written to the encrypted volume, its hash signature will change. So if we go about checking for errors, or checking data integrity, I should have said, the script will ask us for a backup hash. So if I put this one here, now it's recomputing the hash and they won't match. If I run this same command again, but with the actual most recent hash, it will return okay. So that is really important. If we're going to be putting those backups in safety deposit boxes at friend's house or whatever, we want to have a way of knowing if the backup is still good, if the data has been victim to data degradation, or if someone has tampered with it. So hashes are the solution to that. Okay, so that's all for the guide. Now, a last thing that I want to share with you guys is the following, and I am super excited to share this with you guys today. Peer review, in my opinion, is one of the most important parts of any form of research. Humans tend to be biased. They tend to go for self-fulfilling prophecies. Everything that I share with you guys, I put in a lot of time researching it, asking questions on Stack Exchange to make sure that the information is accurate. But you don't have exposure to this. How do you know that you can trust me? And that's actually a good question. Now, solutions to trust issues such as those often point towards something called a web of trust. I think I've discussed this earlier in the series, but a web of trust is when multiple parties can sign each other's public keys, or in the context of the privacy guides, sign a specific guide. And that's kind of a way for other security and privacy researchers to vet my work. And to me, that is super important. So something that has changed in the CMS here is we now have a reviewers section. And that means that Alex has actually signed on that specific guide. So I'll show you guys how this works. If we go on github.com/Knutson and we go about opening the privacy guides, if we look at the different commits here, we can see that Serpent27, which is Alex's handle on GitHub, we can see that, first of all, this commit was signed. So cryptographically, we know that Alex is actually the person who committed this. I cannot impersonate him. And we can see by looking at this that he did review the specific guide, and he himself added himself as a reviewer, signing this specific guide. So that's a way for you guys to know that I'm not the only eyes on this content, that other privacy and security researchers have vetted it. And by the way, if you're a privacy and security researcher with a public profile, have a look at the docs. So there are a few things that you guys can do. Actually, not only privacy and security researchers, there's a few things that you guys can do on GitHub that is super helpful. First things first, if you value the project, please star the repo. So when you go on the repo here, there's this little star button. You need a GitHub account for that. But if a lot of people star a repo, it's a way of showing the community that this content or this code is appreciated, is valued by the community. So that's super helpful. Another thing you can do is, if you're a privacy or a security researcher, or if you have a recommendation on how to harden those guides, please submit an issue on GitHub, and recommendations will be embedded in the guides. If you found a security vulnerability, please report it using my PGP public key and my email found on sunknutson.com. So if we go here, we can see that the PGP public key is available here. Its fingerprint is this, and my email is found here on the little envelope. Now, by the way, if ever you want to make sure that this is actually my key, if you go on GitHub, you can see that my key is available here. And if we go on YouTube, and if we go in YouTube on About or something, my key's fingerprint is there as well. So you can confirm that, you know, that fingerprint is actually mine using those different websites. Now, if you're a fellow privacy and a security researcher, please peer review and sign a guide. Now, I did put instructions here on how to do it. It's pretty simple. You need to clone the repository, then check out draft. That's the branch for peer review. Review a guide, submit recommendations using issues, and once issues have been closed, you can append yourself to reviewers and commit that PR using a signed commit. That's how we're establishing this web of trust using cryptographic signatures. Heads up, in order to establish a web of trust, peer reviewers must have public-facing track records and will be background checked. Anonymous contributions are very welcomed, but they don't help in the context of a web of trust, so only privacy and security researchers with a published track record will be considered for official peer reviews. All right, so that was a lot. So that's all I have for you today. Hopefully this was helpful. It gave you a little bit of perspective on the effort that's put into maintaining the reference material. If you have questions, drop them in the comments, and I'll see you soon for the next Privacy Guides episode. Bye-bye.